So it's not the charge of our panel to evaluate UAP evidence, but part of our statement of task is to assess the scientific analysis techniques that are available. You don't have to start it just yet, and how we might use them to determine physical constraints on UAP. The UAP reports with the most detailed contextual information are the ones from the Navy aviators, and they're using a combination of ranging and infrared imaging information. And for these cases, we can directly calculate critical parameters of a UAP, such as altitude and velocity, under certain assumptions. And it's, the main point I want to make here is that this multi-sensor approach is absolutely critical to charting a path forward for UAP investigations, and that pertains to NASA as well. So I'm going to provide one example here just to illustrate the crucial role of science and scientific analysis, and the role of scientific analysis to avoid misinterpretation in some sense. Next build. Just hit space. Yeah, okay, so this is, this video was recorded by pilots deployed from the aircraft carrier USS Theodore Roosevelt in 2015. The example has been given the nickname "Go Fast" because it gives an impression of an object moving very rapidly against the ocean surface. And the question is this impression correct? And if not, what can we say quantitatively about what that object is doing in kind of Earth-centered coordinate system? Fortunately, the information needed to determine the altitude and velocity of this object is contained on the display. So go ahead and next. And this includes the elevation angle of the camera, the azimuth angle of the camera, the target range in nautical miles, aircraft altitude, the time reference in seconds, indicated airspeed in knots. This information in this video in particular has been discussed quite a bit on the web. So let's begin with the object altitude. Next, please. So knowing the jet's altitude and the bearing to the target, we can apply basic trigonometry to figure out where that object is in altitude space. And it turns out to be, provided the range information is accurate, which can have some uncertainties associated with it, but the object appears to be at about 13,000 feet. An important aspect of this here is that it's sort of midway between the jet and the ocean. So it's the ocean that looks like it's right behind it is actually 4.2 miles away. And this is our first indication that some or most of the motion that we observe, the apparent motion of the object, is in fact due to the rapid motion of the sensing platform, which is about 430 miles per hour in this case. But we don't have to guess about this. So we have enough information on this display to actually reconstruct the encounter. Go to the next slide, please. And so this is what this is. This is using additional information on the screen, including the time axis. And so we know that this aircraft is banking about 15 degrees left, and you can compute through a simple calculator the approximate radius of curvature of the flight. And the bottom line is, I won't go into detail here, but if you can get the bearing and range to the target at two locations with known separation in time, you can figure out how far it moved. And in this case, this object moved about 390 meters in 22 seconds, and that corresponds to a velocity of just 40 miles per hour. And so that's a velocity that's consistent with wind speeds at 13,000 feet. So it's not our task to conjecture what this object is, but it's an example that illustrates the type of data needed to determine critical parameters that will help us identify such objects going forward. In addition to the importance of quantitative analysis, this example also serves to illustrate the kind of cognitive bias we have to contend with for UAPs recorded from unfamiliar perspectives. And Sean Kirkpatrick showed another example of that. This is a parallax effect case. Thank you.